Okay, let's look at number 9 on the exam. Again, I apologize. I'm fighting a cold still, so my voice is probably sounding a little bit strange, but we'll get through it anyway. Number 9 is asking to find the most acidic hydrogen in the molecule below, and it's asking to clearly explain and show why it's the most acidic hydrogen. Now remember, whenever I'm asking you guys to explain why something's the most acidic, um, what I'm asking you really to do there is, make it act like an acid, and then show me how it's stabilizing that charge, right? So show me why the conjugate base is stabilized, or why the minus charge is going to be stabilized afterwards. That's really what it's asking. But let's tackle the first part here, right? Identify the most acidic hydrogen. So we really have a couple of options, right? We've got our alcohol, we've got our carboxylic acid, and then we've got this group down here, okay? And if we want to get super technical, I guess we could look at the hydrogen that's bound to the aromatic ring, and even maybe look at the hydrogens that are bound to the alkyl ring, the alkyl chain there. Just to be honest, right, you're rarely are we really going to be deprotonating a hydrogen that's bound to a carbon? You're going to need some pretty strict conditions for that. We can do it, and we'll talk about it as we go along in the semester. But for the moment, if we're talking about hydrogens bound to a carbon, you've got to be under very strict conditions to kind of deprotonate those hydrogens there. So really, we can eliminate, those the hydrogens bound to the carbons themselves, and so we're left with hydrogen bound to an oxygen. We can eliminate a little bit more and say, okay, we've got an alcohol versus a carboxylic acid, right? An alcohol versus a carboxylic acid. It's probably a good hint that if it's got acid in the name, it's going to be fairly acidic. And going through the homework and the practice, hopefully we've seen that alcohols can be acidic. They've got a pKa, anywhere from about 15 to 17, kind of depending. But carboxylic acids, those are pretty low. We can get pKs about 4 or 3, or even down to 0 in some cases. So if we look at our pKa tables, right, we can see that there's a large difference between the acidity of an alcohol versus a carboxylic acid. And so let's eliminate our alcohol there, right? Between the option of the alcohol and a carboxylic acid, we can see that there is too large of a difference for that alcohol to make to be the most acidic in this case. Okay, so now we're left with these two options. So let's scroll down to our pKa table. Okay, here we are. And let's orient ourselves a bit. So we need to try and find any information that we can here. All right, so if we look in orange, right, there's a generic carboxylic acid right there. I got a pKa of about 5. That's useful information to know. If we look around, let's see, where did it go? I know it was on here. Here it is, okay? If you look here, right, there is a generic pKa for that sulfate group, right, the aryl sulfate group with a hydrogen on it, right, AR's aryl SO3 and then a hydrogen. So just by looking at our pKa table, what color did I have that? Excuse me, green, okay? So let me put this in green here. Okay, so just by looking at our pKa table, we see that there is a big difference in pKa between a carboxylic acid and that aryl sulfate group there. So minus 6.5 to 5, right? So why is that aryl sulfate so much more acidic than a carboxylic acid is going to be? So let's go take a quick look at that. Let's make that aryl sulfate act like an acid, which means I'm just going to abbreviate here while we're going through our answer. I'm going to make it act like an acid. So it is going to deprotonate, right? So we lost our acidic hydrogen. We can say minus, right, our H plus here. We lost our acidic hydrogen. Now we've got our negative charge there on that oxygen. Anytime we're looking to stabilize charges, we go through our same litany of things. We look for electronegativity. We look for radius of an atom. We look for resonance. We look for inductive effects. Any of those kind of things that we've talked about in lecture about how to stabilize that minus charge. In this case, we've got a negative charge, and next door we've got some pi bonds. So we are going to be dealing with resonance. So let's draw resonance structures. There's one. I'm going to abbreviate my pi bonds there in the ring. Okay, we'll do that. We used green to make a pi bond. We turned that into a lone pair, so we got green there. So we shift our minus over here. Continuing on, let's take that. Whoops, I'm sorry, I forgot about our pi bond over here. Okay, drop a pi bond, move a pi bond. Okay. Sulfur, 3 oxygens. Remember, in a resonance structure, the position of the atoms don't change. The pi bonds and the lone pairs do. Or they might, I should really say, if we want to be a little bit more generic about it. We've got our green pi bond here, and we fill in the rest of our lone pairs, minus charge here on that oxygen now. Right, so we can spread that minus charge over 3 of those oxygens. We got some very nice equivalent resonance structures. So we got 3 equivalent resonance structures here. If we went and very quickly drew, let's say that we're looking at the stability of our carboxylic acid, right? We would have that guy here, and we could draw resonance where we would end up with this. So we have 2 equivalent resonance structures here. We have 3 equivalent resonance structures up there with that sulfate group. So just by qualitatively looking at this, we can draw more equivalent resonance structures with the sulfate, which would help spread that minus charge out more, which would make it a delocalized negative charge. If we delocalize the minus charge, right, we're making weak base, and weak bases come from strong acids. Okay? So we looked at the functional groups that we had. We checked our pKa table. We made them act like acids when we did a qualitative analysis of the stability of that minus charge. And we will finish this up in the next recording then.